Black holes are extremely hard to see. They are objects so extreme and their effects on their surroundings so unequivocal, virtually nothing escapes their grasp. When anything gets close enough to a black hole and passes across its event horizon, there is no known way to escape its capture. Stars, planets, dust, gas, even entire galaxies can be devoured by these quiet, deadly celestial traps. Until very recently, we didn't know for certain that they even existed. Black holes were theorized as an extreme limit in Einstein's theory of general relativity, but not until the detection of gravitational waves resulting from a black hole merger were they actually proven to exist. The primary way astronomers see a black hole is by observing the effect it has on things around it. The earliest black holes were detected by observing powerful jets emitting by infalling material from a nearby unlucky star. These black holes were the size of stars, roughly 30 to 100 times the mass of our Sun. Later, we saw powerful gamma-ray jets from the violently active centers of galaxies created as entire stars fell victim to supermassive black holes millions of times larger than the Sun. Since black holes are so dark and emit no light or radiation of their own, we can really only see them when they are near enough to something we can see. Stars, nebulae, interstellar gas and dust all become very bright just before they fall in, their beacons of radiation becoming the celestial tombstones of its victim. The number of black holes that we know about come to us through these indirect methods of interacting and destroying those things we can see. But that's not all of the black holes that are out there. There are many more lurking in the void, all by themselves, quiet and completely dark. Sometimes, if we're lucky, we can find a lone black hole as it passes in front of a star or galaxy in our line of sight. The light from the distant background body is bent around the boundary of the infinite gravitational pull of the black hole, in an effect known as gravitational lensing. Useful for detecting primarily stellar-sized black holes, these effects are very hard to see, and timing is important. We must have telescopes pointed in their direction as they are passing in front of the background object. We must be looking in the right place at the right time. Otherwise, we miss it entirely. Still, astronomers have found a few black holes using this method. There are so many more black holes we don't know about. We need more ways to find them. Luckily, in September 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, introduced a new window to the universe that helps us see naked black holes in a brand new way: gravitational waves. Predicted by Einstein 100 years earlier, they had never been detected. Their signal is so faint that there was no known technology available to show them to us. Until now. Gravitational waves are generated when two extremely massive objects come together. Objects like black holes. This computer simulation shows the warping of space and time around two colliding black holes. This event was actually observed by LIGO on September 14, 2015, by seeing the gravitational waves created in the encounter. The colored surface is the space of our universe as viewed from a hypothetical, flat, higher dimensional universe in which our own universe is embedded. Our universe looks like a warped two-dimensional sheet because one of its three dimensions has been removed. Around each black hole, space bends downward in a steep funnel shape, a warping produced by the black hole's huge mass. Near the black holes, the colors depict the rate at which time flows. In the green regions outside the holes, time flows at its normal rate. In the yellow region, it is slowed by 20 or 30%. In the red regions, time is slowed extremely. Far from the holes, the blue and purple bands depict outgoing gravitational waves produced by the black hole's orbital movement and collision. Our universe's space, as seen from this hypothetical higher dimensional universe, is dragged into motion by the orbital movement of the black holes and by their gravity as well as their spins. This motion of space is depicted by silver arrows, and it causes the plane of the orbit to precess gradually. The bottom portion of the simulation shows the waveform, or wave shape, of the emitted gravitational waves. The gravitational waves carry away energy, causing the black holes to spiral inward and collide. Here, space-time is unimaginably distorted. The shapes of space and time oscillate briefly, but wildly, and then settle down into the quiescent state of a merged black hole. We see the gravitational waves of the collision propagating out into the universe. This collision and wild oscillations constitute a storm in the fabric of space-time. A very brief but enormously powerful storm. During the storm, the power output in gravitational waves is far greater than the luminosity of all the stars in our observable universe put together. In other words, this collision of two black holes, each the size of a large city on Earth, is the most powerful explosion that astronomers have ever seen, aside from the universe's birth in the Big Bang. Our new ability to detect and see gravitational waves promises to increase the census of known black holes in the universe. We can now see black holes as they collide with one another, something we could not do before. With this discovery, gravitational waves proves definitively that black holes do indeed exist, and we need not invoke some strange mathematics to explain the extraordinary energy bursts we see at the centers of galaxies and some nearby stars. That black holes exist, there is no longer any doubt. But an important question remains. Where are they?